Welcome to this explainer. Today, we're diving into a monumental shift in artificial intelligence. We're unpacking a 2021 breakthrough from OpenAI that literally changed how machines perceive the world. We're talking about CLIP. Now, if you've ever been completely blown away by image generators like DALL or Stable Diffusion, well, you're essentially looking at the downstream magic of CLIP. It's the foundational brain connecting text to images. So, if you're looking to understand the core architecture driving modern generative AI, you are in exactly the right place. Let's get into it.
To really appreciate this breakthrough, we gotta ask a pretty fundamental question first. How does AI actually understand what it sees? For the longest time, traditional supervised learning was the absolute gold standard, right? But it had a massive bottleneck. You had to painstakingly train a model on highly specific human-labeled data. It was slow, it was limited. But then came this concept of large-scale weak supervision. This is the exact same methodology that made text models like GPT-3 so incredibly powerful without needing task-specific training. The creators of CLIP realized, hey, we could leverage this exact same methodology for vision.
Okay, let's dive into this. To understand how it works, let's look at the name itself, CLIP. It stands for Contrastive Language-Image Pretraining. It's a zero-shot multimodal model. But, what does that actually mean for us? Unlike older models, CLIP doesn't just look at pictures, and it doesn't just read text. It jointly pre-trains both the image and the text together. It predicts the most relevant text caption for an image, and it does this without being explicitly optimized for any one particular task. Basically, it learns to recognize objects it was never explicitly taught to see. It's like a giant puzzle coming together on its own.
Now, to achieve this kind of generalization, you need data, and I mean a staggering amount of data, 400 million. That is the number of image and text pairs that CLIP was pre-trained on. To put that into perspective, the famous ImageNet dataset, the one that drove the previous era of computer vision, contains about 1.2 million images. So by using 400 million pairs scraped from the internet, the creators made a very conscious trade-off. They traded highly supervised, perfect data for massive, overwhelming data volume, weak supervision at an absolutely unprecedented scale.
But processing that absolute ocean of data requires sheer computational horsepower. Training CLIP took 256 V100 GPUs running continuously for 2 full weeks. If you were to say run this on demand using AWS SageMaker, that compute time would cost you roughly $200,000. No joke. And to make the learning stable across all 400 million pairs, they had to use a massive mini-batch size. We're talking 32,768 images at a single time. So yeah, this was definitely not some lightweight experiment.
Under the hood, though, CLIP is remarkably architecture agnostic. It essentially features two separate brains learning to speak the exact same language. On the image side, it computes embeddings using proven models like ResNet 50, ResNet 101, or a vision transformer. Then, on the text side, it pairs that with a powerful transformer architecture. We're looking at 63 million parameters, 12 layers, 512 hidden layers, and 9 attention heads with masked self-attention to process the language. Both sides are trained entirely from scratch, seamlessly combining these two distinct, powerful capabilities into one working system.
Section 2, Playing the Matching Game, the Mechanics of Contrastive Pretraining.
And this brilliantly illustrates exactly what we're talking about. Think of contrastive learning as a massive, high-speed matching game. The AI's only real job is to tell the difference between similar things and dissimilar things. If we have a batch of images and their corresponding text, we plot them on an n-by-n matrix. The model computes the pairwise cosine similarity, which is basically just a measure of how close the text and image are in the AI's mind. The overarching goal? Maximize that diagonal line right down the center, where image 1 matches text 1. And at the exact same time, using symmetric cross-entropy loss, it actively minimizes the scores in all those off-diagonal cells, where the image and text just don't belong together.
The whole process is incredibly elegant. Step 1, the model takes a batch of image and text pairs. Step 2, it passes them through their respective encoders. In Step 3, the image encoder computes visual vectors, while in Step 4, the text encoder squashes textual descriptions into text embeddings. This forms 2 distinct matrices. For Step 5, it multiplies these matrices together to get the n-by-n pairwise cosine similarities. And finally, Step 6, it maximizes the similarity right along that diagonal center line. It's literally just rewarding the AI for finding the perfect text-image pair in both directions, image to text and text to image.
Section 3. The Zero-Shot Superpower, Surpassing Supervised Learning.
This is where CLIP goes from being a clever matching game to an absolute powerhouse in the world of AI. We mentioned zero-shot earlier, right? Well, this means CLIP can recognize and classify objects in completely new images even if it hasn't explicitly seen those objects during its pretraining. It does this by using the class name, say a specific dog breed, as the text caption. Then it computes the pairwise cosine similarity to choose the highest match. It performs just as well as fully supervised models trained strictly on ImageNet, without ever needing that specialized training data. Plus, it cleverly caches the input text embeddings to save massive amounts of compute time for the rest of the images. It's a real game changer.
Now, if zero-shot isn't quite enough for a highly specialized task, there's few-shot clip. This allows the model to classify entirely new objects with only a tiny handful of labeled examples through a quick fine-tuning process. So if you're in a situation where you have very limited labeled data, but you need rapid adaptation to new classes, few-shot clip gives you a highly efficient, elegant alternative to training a whole model from scratch.
Section 4. Clip versus Humans, the Oxford IIT PETS experiment. Let's set the stakes here and see how this architecture actually stacks up against human perception. Researchers ran this fascinating test using the Oxford IIT PETS dataset. The task was simple. Look at an image and select which of the 37 cat or dog breed captions best matched it. They pitted 5 human subjects against Clip, and when the results came back, no way. Zero-shot Clip astonishingly outperformed zero-shot humans 100% of the time. And it doesn't stop there. Zero-shot Clip even beat humans who were given a 1- or 2-shot advantage, meaning the humans actually got to see a couple of examples first. The machine's ability to cross-reference visual features with textual understanding is frankly superhuman in these specific categorization tasks.
Section 5. Flaws and the Future. Where the Model Stumbles.
So, the crucial point is, despite these incredible feats, Clip is not perfect. Let's bring this back down to earth for a second. The authors of the paper were very transparent about the model's limitations. First off, it suffers from polysemy. That basically means it struggles when words have multiple meanings without surrounding context. Like the word boxer. Is it the dog breed or is it the athlete? Without more text, Clip kind of gets confused. Secondly, it really struggles with handwriting detection, especially handwritten digits. Actually, scratch that. It isn't the fundamental flaw in the architecture itself, but rather a reflection of the training data. It simply didn't see enough handwritten numbers in its 400 million pairs. But, better contextual data sets and more varied handwriting data could easily patch these blind spots in the future. Okay, let's summarize the massive paradigm shifts we've covered in this explainer. Clip gave us the ability to pre-train image and text together. It delivered zero-shot performance that matches heavily supervised models, completely eliminating the need for task-specific datasets. And crucially, OpenAI made the model and its weights completely open source, building it on a computationally friendly architecture. These contributions right here, these are exactly why Clip became the indispensable backbone of the modern generative AI revolution.
Which leaves us with this final, provocative thought. We've seen how effectively Clip maps language to vision, even outperforming us in specialized categorization. So if an AI can play a high-speed matching game better than human vision, what part of human perception will machines map out next? Thank you so much for joining me for this explainer. I really hope this deep dive has illuminated the brilliant mechanics inside Clip, and I highly encourage you to keep exploring the foundational architecture of AI. There is always more to learn.